तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so let us resume our discussion of rotations in 3-dimensional space and then go on to understand what the rotation group in 3 dimensions looks like. So our target, immediate target, is to find out the parameter space of the special orthogonal group, the group of proper rotations in 3 dimensions. So ordinary Euclidean 3-dimensional space, and we would like to understand what the properties of rotations in 3-dimensional space are. Now of course I can represent these rotations by orthogonal matrices on the real numbers with real entries with determinant equal to +1. As you know, if I include improper rotations, namely those which include parity for instance or reflections about some plane, then the determinant could be -1. So SO3 is that portion of O3, that portion of the group of orthogonal matrices 3 by 3 matrices which has determinant +1. O3 itself will comprise of matrices which have determinant either +1 or -1, nothing else is possible for an orthogonal matrix, and the portion we are interested in is that portion which can be continuously found from the identity transformation. No rotation at all means determinant +1, it is a unit operator, and we would like to find out what this group looks like, what is the Lie algebra of this group, what is its structure and so on. Now the first thing we should do is find out how do you parameterize this group. Now clearly since SON has n times n minus 1 over 2 independent real parameters, SO3 has 3 real parameters. Okay. You could regard these 3 as the 3 Euler angles. So if you want to go from any coordinate system of this kind, this is x, y, z, and you want to rotate this coordinate system and go to a new set of coordinates x prime, y prime, x prime, y prime, z prime by some arbitrary rotation, we can do so in many ways. You can reach the primed coordinate system from the unprimed one in any number of ways, many prescriptions, not unique or anything like that. You could rotate first about the x axis, then about the z axis, then again about the new x axis. That is one possible set of Euler angles, and you have many such possible sets. What is unchanged is that you need 3 angles. So a rotation of this kind would be represented when acting on coordinates, would be represented by a 3 by 3 orthogonal matrix parameterized by 3 Euler angles, for instance. Okay. But that is not the most convenient way of parameterizing a rotation for our present purposes. There is a slightly better way of doing this, and that is the following. Any rotation like this could always be regarded as a rotation of the original coordinate system about some axis which is specified by the chalk through a certain angle. So I identify some axis in space and then I rotate through an angle psi, for example, and that gives me the new coordinate system. So I can parameterize these either by 3 Euler angles or by n and psi. This is the axis of rotation, and this guy is the angle of rotation. Is this clear? So I could always choose, if I want to go from here to that coordinate system, there is some axis in space pointing along like this, and about that axis I rotate in this fashion. In the plane perpendicular to this axis I rotate through an angle psi and I reach the new orientation. So again I need 3 parameters because this angle is one parameter, the amount of rotation, but to specify an axis in space with respect to the original coordinate system, I want to specify the direction of this arrow. I need a latitude and a longitude. It is a unit vector, therefore I need just a polar angle and an azimuthal angle to tell me where this point is, where the tip is. So once again I have 2 parameters here and I have 1 parameter here, that gives me the same set of 3 parameters. And then having done this, let me represent the rotation by r of n comma psi. This is now a 3 by 3 matrix which will act on x, y, z and give you x prime, y prime and z prime as linear combinations of x, y, z. And what we know about r is that it is orthogonal and it has got determinant +1. Okay. Now I would like to find out what the parameter space is like. What is the space of these 3 angles? Right. Well, clearly this unit vector n is specified by a polar angle theta and an azimuthal angle phi. Theta runs from 0 to pi and phi runs from 0 to 2 pi, and psi itself, the rotation, amount of rotation in this plane is 0 to 2 pi. So that is my range of n, the parameters specifying n and psi. But let us see how to represent this in pictures. After all, it is a 3-dimensional space and I should be able to draw a picture and tell you here is the 3-dimensional space. So let us draw a sphere, and this is the space of rotations. It is not the physical 3-dimensional space, it is the space of rotations, namely the space in which the components of n and psi live, okay, that is 3-dimensional. Okay. So I draw a solid sphere, and now the convention is that from this origin any direction like this is the direction of this vector m. So I move in any direction in this solid sphere and that tells me the direction of the axis of rotation. Clearly all 4 pi solid angle is covered by this, all possible axes are covered by this. But in addition I also say that the distance from the origin to the point in this space is psi. That is one way of parameterizing it. So if I say I go from here up to this point, this is the amount of angle by which I rotate. So what should the radius of this sphere be to cover all possible rotations? You would say 2 pi, it should be 2 pi because then I go right up to psi equal to 2 pi. But then a magical property of 3 dimensions takes over, for which I will need a solid object to demonstrate it. So if you would pass me the phone, I would try to demonstrate this for you. So look at what happens here. Now let us look at this object, and here is something which conveniently looks like an arrow. So let me draw a little arrow here to show you where. Let me draw an arrow here. So I have drawn an arrow on this, and now I start like this arrow pointing upwards looking at me, and I am going to rotate about this vertical axis through pi in the counterclockwise sense, in the positive sense. So I rotate and there is your arrow out there. But then this was the original configuration, and I rotate by pi about the vertical axis pointing upwards and I have reached this configuration. But then I could also rotate about the opposite axis again through pi. So if I rotate in the positive sense about the opposite axis, I rotate like this and I reach the same configuration. So this tells you that in 3-dimensional space, rotation by pi about an axis in the positive sense is equivalent to rotation by pi in the again in the positive sense about the opposite axis. This immediately says you do not need a radius of 2 pi, a radius of pi is enough, because you can cover all possible rotations up to pi here and all possible rotations up to pi here, and that has covered your full 2 pi. So this space really has the radius, the size of this radius, this length here need be only pi, not 2 pi, because you have covered everything, this full circle, either by rotating about the axis pointing upwards or by rotating about the axis pointing downwards. And since this n unit vector is over all solid angles, it covers all possible directions. But more than that, something more than that happens. So you would say, aha, this space of rotations is very, very simple. It is a solid sphere, it is a 3-dimensional manifold, so it is solid sphere of radius pi, with the understanding that from the origin, from the center, going in any direction to any particular point gives me the axis of rotation, and the distance I travel gives me the amount of rotation. But the unfortunate thing is, or the fortunate, whichever way you look at it, is you saw just now that a rotation by pi about a vertical axis is equal to a rotation by pi about the opposite axis. Therefore this space is not as simple as it looks. This point is mathematically the same as the antipodal point, because they both represent the same physical rotation, because it took the solid object to a new orientation by 2 different ways and gave the same final orientation. So both of these points are exactly the same point. It is as if there is an invisible thread connecting these two, they have to be identified. But that is true for every point on the surface. It is true for this point, that point is mathematically identical to this point. It is not true for a point which is infinitesimally close to the surface but not on the surface. That corresponds to a rotation by an angle little less than pi, and that is very different from this. This identity happens only if you go up to pi, which you have to in order to cover all possibilities. So it says that there is some kind of invisible thread connecting these 2 points, some kind of thing connecting these 2 points, and so on. Every point on this surface is identified, is mathematically the same as the antipodal point. Now such a surface, such an object cannot be written down in 3-dimensional Euclidean space, that is why I am not able to draw it there. Okay. This space is complicated, it cannot be, you cannot embed it in 3 Euclidean dimensions. There are lots of such objects, you need higher dimensionality to be able to represent this object, to see it and so on, but we have the benefit of only 3 physical dimensions to play with. But mathematically we can identify these 2 points. Then the question arises, what sort of space is this? What is the connectivity of this space? Is it simply connected or not? Now if those identifications on the surface did not exist, this is just a solid sphere, and therefore every closed path in this solid sphere can be shrunk to a point without leaving the sphere, and the space would be simply connected. But that is not true here. This space is not simply connected, it is doubly connected, and let me now show you why it is doubly connected. Because there are lots of closed paths in it which would do the following. I could start at some point and then take a little path like this, closed path, which would say I look at a sequence of rotations of 3-dimensional space of my axes specified by this point or this point or this point or this point, etc., and I come back. This sequence of rotations, since I come back, finally can be reduced, can be shrunk like a rubber band to a point, which means I do not do any rotation at all. I just, where I am, I start with this point and I end with that point, and that is it. So there is a class of closed paths which can be shrunk to a point, but there is another class which cannot be shrunk to a point, and that class is the following. I start at the origin, I do a sequence of rotations till I hit the surface. So this is my path in the parameter space, but this point is the same as that point, and therefore if I start here and go back, this is a closed path, because it starts at O, goes to this point but that is the same as the other point and comes back to O, and this is a closed path in this space. But you cannot shrink this to a point, because to do so I would start moving this point. If I move it here, perversely enough this fellow starts moving there, and there is no way I can close this. So it is just not possible to close this physical path, but there is one way in which I can do it, and that is I retrace the path once again. What does that mean? What is this physically meant? It says you go the full pi and then you come back and come this thing. So that is a full rotation, a complete rotation by 2 pi, because you have really gone like this and then you have gone like this. So this is a 2 pi rotation. On the other hand, I could do the following. I do a 2 pi rotation once again. So I start here, I start at this point, go up to this point, let us call it P1, that is the same as this guy here Q1, I come back here, and then I go once again here and do this. Now look at this path, I have traced this closed path twice. Not like this, I start here, I do this and come back. But what is this equivalent to? Let me draw this for clarity, it has to pass through this point in each case. Now let me draw this for clarity by separating them slightly, so it looks like this. There is one path which was P1 and this was Q1. So it started here, went up to that point, which meant you ended up here and you came here and you went here, and I start once again and do this P2, but that is the same as Q2, and then I come back. I have shown them a little separate just for clarity. If I start distorting P1, Q1 will start moving in this direction always, but this is a path which has gone twice through this point, and certainly I can rewrite it like this. So certainly I can take this point and then separate it out in this fashion. So this is supposed to be diametrically opposite. So this is P1, P2, this is Q2, Q1. So notice that at this point I can attach this piece from Q2 to this piece up to P1, and this piece from Q1 to the origin to O I can attach to origin to P2. And once I do that I can separate the two, because I start moving P1, Q1 moves, that is fine, no problem, but I can move Q2 up here, P2 moves, that is no problem, and after this distortion this path can be made to look like this. And then of course each of these can be brought arbitrarily close to each other and knocked off to a point. Okay. So it actually closes. This path is shrinkable to a point. So it is clear that in this space there are closed paths such that you have to do a rotation about 4 pi before you reach the original configuration. Although there are lots of paths where you have to do a rotation about 2 pi and you are back to the starting point, it is clear that there are objects, as there will be representations as we will see, which would come back to their own original values only if you rotate by 4 pi, make 2 complete rotations instead of 1. The technical way of saying this is that pi 1 of SO3 is not equal to the trivial group with just one element, it is not simply connected, nor is it Z, nor is it the set of integers which is what S1 was. Pi 1 of SO3 has 2 elements. There are 2 equivalence classes of closed paths, those which can be shrunk to a closed path to a single point immediately, and those which can be shrunk to a point only after twice traversing the path. Therefore there are 2 equivalence classes, and this group is isomorphic to the group of integers modulo 2, the cyclic group of order 2, and we say that SO3 is doubly connected. By that we mean its fundamental group, homotopy group, is Z2. Yeah.
So what if I consider the same thing as hemisphere, I mean the right hand side of the sphere with radius 2π?
Yeah, but you can't get away from the fact that it is a property of 3-dimensional space that a rotation about pi about an axis is mathematically identical to a rotation about pi about the opposite axis. This you can never get away from, no matter what parameterization you choose.
But then will there be an opposite direction?
Yes, why not? In 3-dimensional space there is, because I label points on the sphere in 3 dimensions and there are opposite directions. This is a property of 3-dimensional space, so it is an intrinsic property as it stands and you can't get away with it, from it. There are similar properties in higher dimensions. I should say right away that SON, where n is greater than or equal to 3, is also doubly connected, but SO2 is infinitely connected. SO2 is the fundamental group is Z, so in some sense 2 dimensions is more complicated than 3 and higher dimensions. Okay. This is finally responsible, as we will see, for the existence of bosons and fermions in the universe, this double connectivity. We will see that there are wave functions which would transform like scalars, vectors, tensors and so on, and then there are wave functions which would transform like spinors, which would correspond to half integer spins in quantum mechanics. But right now we are just talking about groups, the structure of this 3-dimensional space. Now what does this imply? What is the covering group? Just as we found that even though S1 was infinitely connected, SO2 was infinitely connected, there was a map from S1 to the real axis, to R1, which was a mapping which went from 1 to many, and the covering group for S1 was in fact R1 itself. The question is, what is the covering group here, the universal covering group? And as the theorem it says that the universal covering group of a Lie group is simply connected, and once things are simply connected we can do many things on it, because we know that the space is very simple to look at, and the answer is found as follows. So now let me show you how to find the covering group of SO3. For this we need a slightly better way of writing down a point in space and of course representing a rotation. So let us look at that map. A point in 3-dimensional space is some R is an element of R3. This stands for XYZ, the XYZ components of any point. Okay. From this R3 there is a map, and the map is as follows. Normally I would write a point R in space as either x comma y comma z, or I would simply write it as a column vector, right, x1 x2 x3. This is the way I would represent it, and then rotations would be represented by R of n and theta, element of SO3. So the point itself is, points are represented by column vectors and the rotations are represented by 3 by 3 orthogonal matrices with determinant 1. Now I come along and say let us not do that, let us make a map from R3 to a different space, a 1-to-1 map. So for every point in R3 there exists an object in this new space, and this space is that of 2 by 2 traceless Hermitian matrices. You can always do this, just as I showed you there were many representations of R1 itself. You could write R1 in terms of a function space, in various ways of writing R1. In exactly the same way there is a map which takes you from R3 to 2 by 2 matrices, and that is as follows. Let me simply write this instead of this let me write it as x3 x1 plus ix2 minus ix2 x1 plus ix2 minus x3. It is clear that for every given x1 x2 x3 there exists a matrix of this kind and vice versa. This matrix is traceless and it is Hermitian because complex conjugate transposes it is equal to its complex conjugate transpose. x1 x2 x3 are real numbers between minus infinity and infinity. Of course you will immediately recognize that this is also the same as r dot sigma, where sigma is the set of Pauli matrices which we talked about a little earlier. So sigma stands for the set of 3 matrices and sigma 1 is 0 1 1 0, sigma 2 is 0 minus I 0 and sigma 3 is 1 0 0 minus 1. And let me call this equal to, for want of a better name, let me just call it capital X. Capital X is a 2 by 2 matrix. So instead of writing vector R in 3 dimensional space I write capital X as this 2 by 2 matrix and I give you the same information. And symbolically r dot sigma stands for x1 sigma 1 plus x2 sigma 2 plus x3 sigma 3. So this here is shorthand for x1 sigma 1 plus x2 sigma 2 plus x3 sigma 3. It is a matrix. It also looks like a scalar product, a dot product, and it is so because sigma actually transforms like a vector under rotation. Sigma itself transforms like a vector, but we will see that a little later. But right now there is nothing to stop me from exchanging this column vector for this 2 by 2 Hermitian traceless matrix here. Then the question is, 2 questions. First, can I invert this map? Namely, if you give me capital X, can you give me this R? Is there a prescription to do that, and is it 1 to 1? Then it would be a 1 to 1 map. And the second question is, what does a rotation do to X? I know what a rotation does to column vector x1 x2 x3. I just write this 3 by 3 orthogonal matrix and I get a new linear combination. What does the opposite, what does it do in terms of X? Well, it turns out that the inverse is quite obvious. This inversion is quite obvious. In fact, it is not hard to show that xi equal to half the trace of x, or let me write this specifically, r dot sigma times sigma I. So I leave you to check out that if you took this matrix and multiplied by sigma 1, sigma 2, sigma 3 in turn and took the trace, half the trace, you would get x1, x2 and x3. So this is the inverse map. Therefore you give me any r dot sigma, any capital X, any Hermitian traceless matrix, and I tell you what the corresponding xi are. Okay. Yeah. Pardon me?
R dot sigma times sigma I.
That's right. So r dot sigma is a matrix. It's this fellow. So this stands for equal to half trace x sigma I, because I have an I here and an I there. So if I want x2, I have to put sigma 2 there, and so on. Okay. Then the question is, how is this represented? How is this rotation represented as it acts on x, capital X? The answer turns out to be that r of n and psi, let us call it psi, the angle by which I rotate, because I would like to keep theta for the polar angle of the axis n, theta and phi. So let us call the angle by which you rotate, through which you rotate, as psi. Instead of this you represent it by a unitary matrix U of again parameterized by n and psi, which happens to be e to the minus I n dot sigma psi over 2. Now what sort of object is this U? Remember sigma is a 3 by 3 is a 2 by 2 matrix, it is a Pauli matrices. So you exponentiate it, you still get 2 by 2 matrices. So this quantity U, this object U is again a 2 by 2 matrix finally. It should be, because that is what can act on this. This is what can act on this guy. What sort of matrix is it? Remember n is direction cosines for some unit vector, so they are all real components, psi is real, and sigmas are all Hermitian matrices, and you have e to the power I times real parameters times a Hermitian matrix. What sort of object is that? If you have e to the power I, a real parameter times a Hermitian matrix here, Hermitian operator here, if I take its Hermitian conjugate, it is going to give me Hermitian conjugate is e to the minus I, alpha is real, h dagger, the Hermitian conjugate, but this is the same as h. So taking the Hermitian conjugate of this guy gives you e to the minus this guy, which is the inverse. So it means that U is a matrix such that U dagger equal to U inverse, and what do you call a matrix? U dagger equal to U inverse, or U dagger equal to identity, unitary matrix. That is the reason I used U. So this guy is unitary. This guy is Hermitian. Yeah. How did I arrive at U? I worked backwards. Okay, there is a systematic way to arrive at U, I did not want to get into that right now, but this is the way you do. If you look at books on classical dynamics, they would treat what are called the Cayley-Klein parameters, and this is essentially what it is. Okay. So right now I am just presenting the result, telling you what it is like. You could ask, can I have other representations and so on, why 2 by 2 and so on and so forth. There is a reason, technical reason for it. This is in some sense the easiest representation. There is infinite number of representations possible. This is the simplest of the lot, and you will see why. Yeah.
Some R.
Yeah.
Then how do we get the form of U?
How do I get U? This is the prescription. You mean if you are given R itself? I haven't written down R itself, I haven't done that. It is a 3 by 3 orthogonal matrix. It is fairly messy. It is in fact much messier than U. You will see that U is fairly straightforward. Towards the end I will go back and show you what R does, how it acts, and it does so in a very interesting way. Okay. So this is now my claim, is that this represents the rotation as it acts on this x. Then the question asked is the following: if you go from R to R prime, so I start with a position of point R, and then I apply rotation, I go to R prime, which is equal to this R of n psi acting on R, where by this I mean the column vector and by this I mean the 3 by 3 matrix. So it goes to some point R prime, which is x prime, y prime, z prime. Then the question is, what does x do? So this guy here is mapped to x, is replaced by x, and obviously under rotation it goes to some x prime. And how is x prime given in terms of x? And the answer is that this is given by U of n psi acting on x, U inverse on n psi. So this is the action of this U, of this representation of the rotation group. This is the action of it. So you give me an x, corresponding to a point in space, and under a rotation represented by u it goes to a new matrix x prime where x prime is given in terms of x by this object. And this is invertible because u has an inverse clearly, and it is clearly invertible. You could write obviously u inverse x prime u is equal to x, goes back in the other direction. Therefore, rotations are represented either by 3 by 3 orthogonal matrices, or they could be represented by 2 by 2 unitary matrices with determinant +1. It is easy to see that the determinant of something like this is +1, because if you set psi equal to 0 you get the identity. So it is the connected part of this group and the determinant is +1. Now the question is this a 1-to-1 map or not, and the answer is it is a 1-to-2 map, because in the space of the u's, here is the space of this u's, space of 2 by 2 unitary matrices with determinant +1. And this is the space of SO3 of all rotation matrices. Then corresponding to a rotation here and some small neighbourhood of it, there exists a u here, so this was an r, but there also exists a minus u. A minus u will give you exactly the same rotation. So in fact it is a 2-to-1 cover. Every point, every physical rotation represented by an element of SO3 is mapped to 2 different u's here, which differ by a sign. And it turns out that that space is the right one, that is the universal cover. We have to show it is simply connected, we also show we have to see what its parameter space is, but we can identify that space. What do you call the space of unitary matrices in n by n matrices on the reals? It is un, and of course if you put an s for determinant then it is the unitary unimodular matrices, and therefore this is SU2. This space is the space of SU2. Okay. So that is what provides the cover. We have to show that it is simply connected. That is not hard to show, because what is the most general form of a 2 by 2 matrix which is unitary and which has unit determinant? Well, you could have an arbitrary complex number alpha here, it is unitary and it must have determinant +1. These conditions are sufficient to show that the most general such matrix that you can have must be of the form some alpha complex number, some beta complex number, but what must appear here is beta star and alpha star, and mod alpha squared plus mod beta squared equal to 1. This is the most general 2 by 2 unitary matrix with determinant +1. It is parameterized by 2 complex numbers alpha and beta, satisfying mod alpha squared plus mod beta squared equal to 1. Okay. But what sort of object is this? It is alpha 1 squared plus alpha 2 squared plus alpha beta 1 squared plus beta 2 squared equal to 1, that in the space of 4 real parameters alpha 1, alpha 2, beta 1, beta 2 is the surface of a sphere of unit radius. So this guy is S3. Okay. So this says that the rotation group in 3 dimensions SO3 has as a universal cover SU2, but SU2 is simply connected. SO3 itself was doubly connected, it has a complicated parameter space, but S3 is simply connected. and I said S3 is also a Lie group, it is in fact SU2. S3 has the structure of a Lie group which is SU2 itself. So this is the origin, and this is the starting point for seeing that there are objects in 3-dimensional space which would have transformation properties under the rotation group such that a rotation of 2 pi brings you back to the same object, and there are other objects where a rotation of 2 pi changes the sign of this object and a rotation of 4 pi brings you back to the same object, and the former are called the tensor representations and the latter are called the spinor representations. That is the origin of spin half, 3 halves and so on when you quantize when you put in quantum mechanics onto this structure. But this is the basic point, this double connectivity here. You could ask what about the covering group for, so let us write the covering groups. You had SO2 and the covering group, universal covering group here for SO2 was R1 itself. This is SO2 or U1, points on the unit circle, or S1. Then you have SO3 and the covering group is SU2. Now you could ask, okay, what about SON, n greater than or equal to 3, n greater than or equal to 4 for example. Well, these are also doubly connected, and the covering groups here are not SUN or anything like that, or SUN minus 1 or anything. The covering groups are called the spin groups. So the covering group here called spin n. That is just a name at the moment, later we will put some more structure to it. Okay. But all these spaces are also doubly connected. Now to go back and answer the earlier question, what does R do? What does R of n comma theta look like? In general it will be a terrible mess. Of course if I rotate about the x axis or the y axis or the z axis, things are simple, but if I rotate about an arbitrary axis it is quite complicated. The 3×3 matrices are given in textbooks, it is quite complicated, but let me write down the answer as to what finally happens to a given vector, and that is not hard to see. There is a systematic way to do this, and that is the following: represent the point R by this matrix X, apply this rotation, so apply u of n psi on X, u inverse of n psi, where u is equal to that. So apply this rotation here, find u inverse which is the same as u dagger, this guy is the same as u dagger, and then you have to multiply 3 2×2 matrices, that gives you x prime, and from x prime go back to r prime, because I know that xi prime equal to half trace x prime sigma I. That will give you the new components. Good exercise, except you must know how to do this, you must know how to write the exponential of this thing here, but that is where the properties of the sigma matrices comes in. The sigma matrices are very very interesting properties, among which is the following fact. You see, we have to do something like e to the I alpha dot sigma, where alpha stands for 3 real numbers. In that case alpha was just psi over 2 times n with a minus sign. But in general, if alpha 1, alpha 2, alpha 3 are 3 real numbers, and I want to do e to the I times alpha 1 sigma 1 plus alpha 2 sigma 2 plus alpha 3 sigma 3, I use the fact that sigma I sigma 1 sigma 2 plus sigma 2 sigma 1 equal to 0 and cyclic permutations. These matrices anti-commute with each other. Moreover, sigma 1 squared equal to sigma 2 squared equal to sigma 3 squared equal to the unit matrix. Then exponentiation is very easy. You have a formula similar to the Euler formula. The Euler formula says e to the I theta is cos theta plus I sin theta. For 2 by 2 matrices there is a similar formula, not for 3 by 3, 4 by 4 or anything, but for 2 by 2 there is a simple formula, and that follows from these properties of the sigma matrices. It is not hard to show that this is equal to cos alpha times I plus I sin alpha over alpha I alpha dot sigma over alpha sin alpha. Where alpha stands for the square root of alpha 1 squared plus alpha 2 squared plus alpha 3 squared. You got to be careful about the i's and so on if the alphas are complex, but if they are all real numbers it is very straightforward. This formula is not very obvious, but it is logical, because you know that any 2 by 2 matrix can be written as a linear combination of the unit matrix and the 3 Pauli matrices. E to the I alpha dot sigma is also a 2 by 2 matrix. Therefore it should also be written writable as a linear combination of the unit matrix and the 3 sigma matrices, and these are the coefficients, and it looks exactly like Euler's formula. Okay. Now given that, all you have to do is to substitute alpha equal to psi over 2 times unit vector n, and that will tell you what u is, and this is just the Hermitian conjugate on this side, and put those matrices, multiply through, and they take this trace, and you go back to what r prime is. That is the fastest way of finding out what r prime is under a finite rotation. Mind you, I have not written down the matrix R itself, that is quite a mess, but why do I need that matrix? I need it only to find out what r prime is, but I am telling you a formula for r prime. There is an even simpler geometric way of doing this heuristically, and that is the following. And that is as follows. So let us suppose this is the axis n, the original frame of reference, this is the axis n, and this is my point r, this point here, and I would like to find out what does r do under a rotation through an angle psi about the axis n. It is quite clear from this figure, this is n, it is quite clear that r is going to move on the surface of a cone of angle psi, of half angle, the angle of half angle which is equal to the angle between r and n, and it is going to move on this, how much it moves depends on what psi is. So let us suppose it ends up at some point like this, r prime. So you have this axis and you have that vector and you rotate, it goes like that. Now the question is, what can r prime depend on? Well, there is the original r and there is the n, and it is a linear transformation, therefore every component of r prime must be a linear combination of the components of r. Look at r and n, they form 2 vectors and they form a plane. Therefore any vector in 3-dimensional space should be expandable along r, along n, and along r cross n. So this whole thing finally, r prime must be equal to something times r itself plus something in the direction of n plus something in the direction of r cross n. That is all it can be, and these somethings must be scalars, they must depend on psi. Now what can happen here is that this term here must also depend on r linearly, so it must be the component of r along n, and therefore you can in fact further reduce it and write this as n dot r on n times something or the other. Now every term is linear in r, agreed? And then if you go through this rigmarole, this long formula, you discover there is a very simple formula which is cos psi r plus 1 minus cos psi n dot r n. Then of course no medals for guessing what the last term is going to be. What should it be? Sin psi. Sin psi. That is it, n cross r, n cross r. So that is the effect of a finite rotation about an axis n through an angle psi on an arbitrary vector r. And after you do this entire rigmarole, this is the answer you would get finally. Okay. So I urge you to check this out, that you really get this answer. Okay. So it is a very simple structure, as you can see, the portion along r, portion along n with component n dot r, and then n cross r. You could also combine this guy, this cos part here along with this, and write it as n cross r. Do that, but they are equivalent ways of writing it. I find this easier to remember. Now you can put in special cases, you can put n along r and see that it does not change at all. If you put n along r, that last term vanishes, and then this guy cancels part of it, and then you end up with cos cancels, and you of course end up with just r itself. So from this you can work back and write what the 3 by 3 matrix is. So I urge you to do that. So take n to have components theta and phi, latitude, polar angle and azimuthal angle, and then find out what that 3 by 3 matrix is. Not the most convenient way of representing rotations, but such as it is, it is a simple orthogonal matrix. Now what I would like to do is ask you a couple of questions which will be useful later on, and then I would like to do the role of symmetry. I would like to shift to symmetry. We have been talking about rotation, so I would like to go to invariance and symmetry. Remember that I pointed out that you have matrices which are unitary look like this, u dagger u equal to I. Elements n by n matrices which are unitary belong to a group of matrices satisfying this, u dagger u equal to I. Now the determinant of such a matrix is a pure phase, it is e to the I theta, and if you insist that the determinant should be +1, you get the SUN group, and that has n squared minus 1 generators. The space of this SU2, for example, the space is a compact space, SU3 is a compact space, closed bounded space. I also pointed out that if you had matrices which satisfied u dagger some other quantity here which was not the unit matrix but something slightly different, I do not remember the notation I use for it, something like G, u equal to G, and this G had a P by P matrix and a Q by Q matrix here in this fashion. This is the unit matrix and this is minus the unit matrix. Then I call the group of matrices satisfying this as belonging to SU P comma Q. With this metric here. So you could ask, we just talked about SU2, these are 2 by 2 matrices. We could also talk about SU1 comma 1. Those would be matrices where this G would be a 1 0 0 minus 1 out here. They would look exactly like this, except that the condition would be alpha squared minus mod beta squared equal to 1. There would be a sign change here. What sort of object is this? It is actually a hyperboloid, it is not a closed sphere, it is a hyperboloid because you have a minus, therefore each of these quantities can become arbitrarily large and cancel each other to give you the difference equal to 1. It is like the difference between an ellipse and a hyperbola. A hyperbola is an open curve, but an ellipse is a closed curve, here, a bounded curve. So a group like this is non-compact. The parameter space goes all the way to infinity, it is not bounded. Therefore this change of metric is highly non-trivial. It goes straight away from a compact group to a non-compact group, and we will see that the Lorentz group, the group of special relativity, is a group in 4 dimensions, space and time, which is the group of pseudo orthogonal matrices 3, 1, 3 space like directions, space like coordinates, and 1 time like coordinate, which would leave a particular kind of quadratic form unchanged. And this is a non-compact group, this guy here, and this would be a group, the group we will focus. It satisfies a relation very similar to this. So if lambda is an element of this group, then it says lambda transpose G lambda equal to G, where this G would be 1 minus 1 minus 1 minus 1. So there would be 1 time like direction and 3 space like directions. Sorry, in this notation it would be Q comma P, the opposite way. So we will do that next when we talk about relativity. This is what we are going to do. But before I do that, I want to come back a little bit to classical mechanics and show you how invariances and symmetries are closely related to each other, and they are related by a theorem called Noether's theorem. I seem to have run out of time. So the connection in fact is you identify a symmetry that leads to an invariance that leads to a conservation principle. It is a crucial thing in all of mechanics, all of field theory, and all of physics itself, and we will explore this connection, and it is summarized in something called Noether's theorem. And next time I will talk about this theorem and show you how in Lagrangian mechanics there is a simple formulation which gives you this conserved quantity directly. So the moment you identify, for instance, I know that the planets move around the sun in a central force, and I know that a central force implies that angular momentum is conserved, and the way I prove it is to say that the rate of change of angular momentum is the torque, and there is no torque in a central force, but it is deeper than that. We would like to understand where does this angular momentum conservation come from. It comes from the spherical symmetry of the system, the fact that all directions are equivalent when you have a central force. So that symmetry leads to the fact that the equations of motion do not change in form under rotations, and that in turn leads to the conservation of angular momentum. So this is the path we need to trace to understand how does a symmetry lead to an invariance, and how does that in turn lead to a conservation law. How do I calculate the quantity that is conserved, and that is what is given by Noether's theorem here. In general, this conservation principle is in the form of a conserved current, a quantity satisfying some continuity equation, and that in turn leads to the conservation of a macroscopic quantity like a charge or something like that. Conservation of mass follows from the equation of continuity. So you get a local statement and then you get a global statement finally, and this is done by Noether's theorem. So this is what we will talk about next. Do this, we will start with simple examples and go on. Okay.